Calc BC?
Yeah.
Okay, and I'm going to work with her on Friday, which is good.
Yeah.
It'll give me a little bit of time to figure out how to explain Taylor polynomials to her.
Yeah.
That's
Sounds
one of the tougher things in Calc BC. In fact, I have another Calc BC student who said that that was absolutely his toughest thing was Taylor polynomials.
Oh. Yeah, sounds
So,
confusing.
but I'll be in shape to help her by tomorrow or Friday. So what are you doing parametric equations and the unit circle?
Yeah. Most of the unit circle makes sense to me, I think. So I would save that for the end. I'm really confused on parametric though.
Let's start. You have some parametric equation problems?
Yeah, I have also a graph that I'm emailing to you right now.
Okay.
So, yeah, that should arrive soon.
Okay.
And, yeah, I will tell you a problem. I have a picture. Okay, so it says a plane is flying at 100 miles per hour on a bearing of 60 degrees.
Okay.
And then part A says to draw a diagram of the motion and to write equations for x and y in terms of t.
Okay. Uh, 60 degrees means 60 degrees east of north, I believe.
Yeah, so 30 degrees?
Well, it depends on what your reference line is. Usually when you're talking airplanes, everything is based on north.
Yeah.
And you said at a bearing of 60 degrees or you said at a bearing of 60 degrees east? What did
On
you
a bearing of 60 degrees.
just that? Okay. So it's clockwise if it's not specified.
Okay.
Okay. If I'd have
So
said
from
negative 60 degrees, it would have had a bearing of northwest instead of northeast, like this thing does. Okay.
okay.
And this axis, well, okay, we'll call this x and y.
Yeah.
That makes this a 30-degree angle. And the magnitude of that vector is 100. And so if I make a triangle like that,
Mhm.
with this dimension being x and this dimension being y, now give me a trig function that gives me
Yeah.
that. In other words, you could say the sine of what
30 degrees.
equals
Um,
sine.
well,
Sine is opposite over hypotenuse.
y over 100?
Uh-huh.
Wait, but how do you know that the 100 goes on the hypotenuse?
Well, because this is also your first introduction to polar coordinates. Kind of like the unit circle, the hypotenuse is 1 all around the unit circle. It does not change sign. It's 1.
Okay.
Okay? And an airplane flies on a vector. So what we're also talking about here are vectors. And one way to plot a vector is on polar coordinates. And if you plot, and polar coordinates fit on top of xy coordinates.
Okay.
Notice that I've drawn the xy coordinates, but this really is a vector.
Okay.
30 degrees counterclockwise from the x-axis.
Yeah.
Okay? So y ends up being equal to 100 times sine of 30. And what y is the vertical measure, the vertical amount flown
Yeah.
based on, actually, excuse me, all of these are going to be vectors. So what y is essentially the vertical rate of speed that the plane is traveling. If the plane is traveling at 100 mph in this direction, I can separate that into a vertical component and a horizontal component.
Okay.
Here's the vertical component right there. The sine of 30 degrees is 1/2. So effectively, the plane is moving in a northerly direction by 50 miles per hour. You with me?
Yeah.
Okay.
Yeah.
Now let's solve for the cosine. What's the cosine of 30 degrees?
It would be, wait, x over 100.
Right. So x is going to be 100 times the cosine of 30 degrees.
And
So
where does he fit in?
in other words, so I've taken this 100-mile-per-hour vector and I've separated it into its horizontal speed and its vertical speed. What is its horizontal speed?
100 times the cosine of 30?
Correct. Cosine of 30 is √3/2. So it's 50√3. So it's going faster horizontally than it is vertically, but that's what you would expect. It's closer to the x-axis than it is to the y-axis. If that was a 45-degree angle, it would be going equal.
Yeah.
Okay? This is a key part, though, in the analysis of this whole problem, is figuring out what its horizontal component is and what its vertical component is. Because the next thing they're going to do is introduce a wind into this equation. And they're going to say a wind is blowing from the east at 20 miles per hour.
Oh.
What's the net effect on what it does to that airplane? And what you do is you subtract. In other words, I know what the horizontal component is. So if the wind is blowing in this direction from the east at 20 miles an hour, well, I know my horizontal component going this way is 50√3.
Yeah.
So the net horizontal movement is going to be 50√3 minus 20.
Okay.
Not going to affect my vertical motion.
Yeah.
But that's how these problems usually work themselves out. In other words, it sounds like you're in the section of not just parametric equations, but vectors and parametric equations.
I don't know.
And they all include trig. So you have to have trig before you can really study vectors and parametric equations. Both of them involve trig.
Yeah.
So how much trig have you had? Refresh me, Zoe. Because usually you get the unit circle at the very beginning.
Of trig?
Uh-huh.
I had, like, in geometry last year, we learned, like, simple, like, cosine, sine, and tangent.
Yeah. Yeah. No, I'm talking about in trig class, when you actually take a full trig class for a full semester, usually the unit circle is where you kind of start.
Well, we learned the unit circle for the first time yesterday.
Oh, okay.
And we have a quiz on it now every year to make sure that we know, like, about it. So I have a quiz on it on Monday.
Okay. So before we get to the unit circle, do you have any other questions on this? Did we answer everything here?
Can you see if you received the graphs that I sent?
Oh, yeah. Let me look here. Got nothing.
I'll see if it sent.
Does it say sent? If it says sending, then it's not sent. You might be having a little bit of internet difficulties also in terms of being able to send attachments with to emails.
I may have put your email in wrong because
Okay,
my
let me write what my email is on the screen. Hold
okay.
on. COWAN.
Okay.
Usually that's the mistake people make is they put E in. No spaces anywhere.
Okay. I'll send it again.
Okay.
All right.
That's all right. Go ahead and send it again, and then maybe we can do another one while we're waiting for it.
Yeah.
I don't want to erase that yet. You got it in your phone?
Yeah, I got it. Thank you.
Okay.
Okay. Let me find. I have a picture in my phone of another problem.
Okay. Let's talk about the unit circle, since you said you're having a quiz on the unit circle.
Yeah.
Let's set aside vectors and parametric equations, because the unit circle is a big topic, and usually it takes me about an hour to properly cover it.
I think I understand most of it.
Okay, well that's good. That's a big help. What I usually do is fill my page with the unit circle, a couple of the special triangles, and SOHCAHTOA, and label the first, second, third, and fourth quadrant, label what the reference angle is in the second, third, and fourth quadrant, and tell everybody memorize that.
Yeah. I got that. I just like have an equation that he gave us that we were supposed to look at the unit circle, I guess, or use the unit circle to find the answer.
Can you solve? Let me give you some points on the unit circle. In other words, if you're having a unit circle exam, is this the exam where you have to give all 16 points on the unit circle?
I don't know. He won't tell us what's on it.
In other words, there's that point, that point, that point, that point, that point, all the way around in each quadrant.
Yeah, probably.
This is based on a 30-degree angle. The thing you have to know is that that is the cosine of x, comma, sine of x. That x and y coordinate, that's what it is. No matter what. Every single point on the unit circle, because it is the unit circle, in other words, these are all radiuses of 1, the x and y coordinate are those values. So you have to know, like, well, there's one point on the unit circle right there, 225 degrees, right?
Yeah.
So if I go all the way around to there, and there's my terminal thing. Okay, so you'd have to know both the sine and the cosine of that. How do you figure those out?
We just did it how like we put points like negative square root of 2 over 2,
Well,
comma negative square root of 2 over 2.
Simplify it for you. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. The two special triangles that will tell you all your trig functions in the first quadrant are your 30-60 and your 45-45.
Yeah.
All you need to know is the dimensions. And then what you do is you take every angle that is not in the first quadrant and you convert it to a first quadrant angle.
Yeah.
For example, and here's something else. What you use is 180 minus theta in the second quadrant. You use theta minus 180 in the third quadrant. And you use 360 minus theta in the fourth quadrant.
I don't know. I don't think we've learned this.
25 is in which quadrant?
225 is in the third quadrant.
Okay, so what's its equivalent? What's its reference angle, which I like to put in parentheses right there.
45.
Okay, now use one of those two triangles down below to figure out what the cosine of 45 is. Don't rationalize it, just give it to me as a ratio, even if it has an irrational denominator.
So 1 over the square root of 2?
Yep. Now, the last thing we need to add is its plus or minus sign. And the other thing I know is that all students take calculus, which tells me what each trig function is in each quadrant. The A stands for all. All 6 trig functions are positive in the first quadrant. The S stands for sine only. Actually, sine and cosecant, but of the main 3, only sine is positive in the second, only tangent in the third, only cosine in the fourth. So what's the plus or minus sign on cosine in the third?
Wait, so is it only positive or only negative?
Only tangent is positive. In other words, these letters stand for the trig function that's positive in that quadrant.
So then the cosine would be negative.
Correct. So I'd put a negative sign in front of that. And that also, if they want to, when they say memorize the unit circle, they want you to give them the x and y coordinates of that. So the x coordinate would be negative 1 over root 2. What's the sign? What's the sine's equivalent first quadrant angle, or what they would call the reference angle? It's 45. What's the sign of 45?
Wouldn't it also be 1 over square root of 2?
And what is its plus or minus sign?
Minus.
Correct. And notice this matches. If I draw a triangle, notice the x measurement is negative and the y measurement is negative. So I would certainly expect both of these coordinates to be negative.
Yeah.
And they are. Both sine and cosine are negative in the third quadrant. And what you're looking at there, here, let me erase this. You don't need to memorize this. But everything else you should memorize.
I don't think we're there yet, though. We just need to know, like, the negative square root of 2 over 2.
Well, trust me, if you're not there, you're going to be there by tomorrow or the next day.
Okay.
Okay? In other words, you are in, correct me if I'm wrong, but you're in trig for the rest of the semester, right?
No, I'm in Algebra 2 honors.
Yeah, but they're going to do a lot more trig than they did in geometry class.
Okay.
The way trig is taught is they might even give you a little bit in Algebra 1 class, and then they give you a little bit more in geometry class. And usually by Algebra 2, they either give you quite a bit more, or if you're in honors, I would suspect that they'll jump right in and you'll get a lot of trig.
Oh, okay.
Unit circle is where it kind of begins.
Okay.
And when they say that they're going to test you on the unit circle, and they may have said that, they may not have. I don't want to waste our hour tonight covering stuff that you haven't really gotten to yet, even though it would be very valuable to you. If I were you, I would take out a picture, your phone right now, and take a picture of what you see.
Okay.
Because you do want to memorize that.
Okay.
Now, there are a couple of other points that are very useful here. Do we know what the x and y coordinate of that one is?
Yes, that one is 1, 0.
Okay. What angle does that represent?
0 degrees.
Okay. So what is the cosine of 0 degrees got to be? Remember the
What?
first? Yes, the x-coordinate is cosine.
Yeah.
What's the sine of 0 degrees got to be?
0.
Okay, and I can go around the horn. This point up there is 0, 1. So if I said to you, what's the cosine of 90 degrees?
It would be 1? No. Wait, it
First
would be
one is the cosine. X-coordinate is the cosine.
0.
In other words, this over here, memorize that.
Yeah, it's
It
0.
goes sine, cosine. It goes cosine, sine. So the first one would be 0, and then the sine of 90 degrees would be 1. Now,
Yeah.
notice that these quadrangles, which is what 90, 0, 180, and 270 are called. Any multiple of 90 is called a quadrangle. You can't easily get those from those two triangles down there. You can certainly get 30, 45, and 60 degrees, but 90 degrees requires you to view it in a very strange way. But you can get all your quadrangles by just looking at those 4 points. What's the coordinates on that point?
On which one?
The one at the 180. In other words, the other thing I really should do is label that 180 degrees. Let's label that 90 degrees. Let's label that 270 degrees.
So at 180 degrees, it's negative 1, 0.
So what's the cosine of 180?
Negative 1.
And the sine of 180?
0.
So that's how you figure out the sine and cosine of your quadrangles.
Yeah.
And I could do the third one also, but let's not do it. I think you understand it
Yeah.
at this point. So between everything I have on this page right now, you can figure out your unit or your unit circle that they want you to memorize. And I don't know whether they want you to do that for your exam on your next trig exam or not. But what it used to mean was memorizing the unit circle, you had to know all 16 points, the x and the y coordinate of all 16 points. So for 30 degrees, you had to know that point. For 45 degrees, you had to know that point. For 60.
We need to know all of that plus more. Like,
okay.
One of them is the sine of negative 1. Sine to the power of negative 1.
That's inverse sine.
Of negative 1.
Inverse trig functions. All right. Can I erase this page?
Yeah.
Let's talk about inverse trig functions for a moment. If the sine of 30 degrees equals 1/2, which it does, we take trig functions of angles to get ratios. Doesn't matter whether it's sine, cosine, tangent, secant, cosecant, cotangent. We take trig functions of angles to get ratios.
Okay.
If this is true, then this is true. The inverse sine of the ratio is equal to the angle. So if you're solving for angles, you're going to use inverse trig functions. If you're solving for numbers, you're usually going to use trig functions. Let me draw the classic triangle that you've known for 3 or 4 years.
Okay.
Bet you don't know what that angle is.
No.
No, they've never taught it to you. It's not significant. But with this, we can figure out what that angle is.
Oh, yeah. Okay.
I have a triangle that I'm trying to solve for an angle. Let's say I needed to know what that angle is. Then I'm going to take the inverse sine of 3/5. Because the sine of that angle is 3/5. So to solve for that angle, I'm going to take the inverse sine of that ratio.
Yeah.
And that turns out to be about 37 degrees. So that's about 37 degrees. But that's not the point. That's not a particular important angle. The whole point, the whole reason I did this was to show you that you can solve for angles using trig. It's not just a question of solving for the dimensions of the sides, but the inverse trig functions are used to solve for angles.
But what if it's the inverse of sine of negative 1/2?
Okay, let's talk about that. Well, we know that's not 30 degrees, right?
Yeah.
Because sine of 30 degrees is positive 1/2.
Yeah.
But there are 3 other quadrants.
Yeah.
Well, in the second quadrant, which would be 150 degrees, would be the equivalent of 30. So I know the sine of 150 is also 1/2, but it's also positive because it's in the second quadrant, sine is positive. So it's not either of those. So let's look at the third quadrant. Well, which angle in the third quadrant? That one right there. And in the fourth quadrant?
330.
Now, this gets a little tricky. If you put this into your calculator, it only gives you minus 30 as an answer. What kind of calculator do you have?
TI Inspire CX CAS.
Go ahead and do that. Go ahead and put the inverse sine of negative 1/2.
Okay.
You'll see what I mean.
I got negative pi over 6.
Okay, you're in radians. So
Oh,
I'm
yeah.
in degrees. That's the same as negative 30 degrees.
Yeah,
That's
I'll
fine.
change.
I don't care that you're in radians. I can switch to radians also. But here's my point. Minus 30 degrees is the same as that. It's coterminal with that, right?
Yeah.
So it really gave us 330 degrees, but it omitted that one. It didn't give us 210. And yet clearly, if I do a 210 degree angle, the sine of that thing is negative 1/2. So therefore, the inverse sine of negative 1/2 should include that. Well, here's what's going on. Your calculator is treating it as a function.
Okay.
Functions can only have one answer. You can't have 2 answers if it's a function.
Okay.
In other words, if it's going to pass the vertical line test. So to even come up with the concept of inverse sine, first of all, the inverse sine is truly the inverse of sine. It's the inverse function.
Yeah.
Okay? But in order to do it, because sine looks like this, well, if I took the inverse of that, it's not going to be a function. In other words, you get the inverse by rotating it about that line right there, y equal x.
Yeah.
It will not pass the vertical line test if I do that. So what they do is they arbitrarily restrict the domain from minus pi over 2 to pi over 2 when they talk about inverse sine.
Okay.
Okay? And if I take that same curve, the sine curve, and this is hard for me to do just artistically, to rotate it about that thing. But you get something, let's see, the sine of pi over 2 is 1, so I know it goes to there. I know that's there. I think it looks something like this. Okay? In other words, by restricting the domain of sine to only go from minus pi over 2 to pi over 2, you end up with a function now when you talk about inverse sine. And your calculator has to have it as a function. It can't give you all these various values that it's actually at. So with sine and tangent, if the argument is positive, it's the first quadrant angle. If the argument is negative, it is the fourth quadrant angle. Tangent does the same thing. It's positive in the first, negative in the fourth. Cosine is not that way. Cosine is positive in the first, negative in the second. So if you put cosine of negative root 3 over 2, it gives you the second quadrant answer, which is 120 degrees. It does not give you the third quadrant answer, which would be 240. But that's out of your calculator. So it's important for us to distinguish the answers you get from your calculator as opposed to the answers you would get if you solved an equation, the sine of x equals negative 1/2. There's a trig equation. Okay?
Okay.
And you can't just use your calculator to solve this. You'll get minus 30 degrees. In other words, if you take the inverse sine of both sides, and that's one way to look at it, incidentally. The left side becomes x, right side becomes this, but now we mean in the whole unit circle, because usually my domain is going from 0 to 2 pi, or 360 degrees. So if your domain is the entire unit circle, then the answer to that equation is both the fourth quadrant and the third quadrant angle. In other words, x would be not only 210, but 330. That would be your answer, even though your calculator wouldn't show you the 210. So this is why you have to be careful. If they say to you, what is this? That is a calculator question.
Okay.
And the answer is minus 30 degrees.
Okay.
But if they say to you the sine of x equals minus 1/2, that's an equation. And that has two solutions. Minus 30 degrees and 210 degrees. Or you could say 210.
Unit circle is the minus 30.
What's that? Yeah, the minus 30 is the same as the 330.
Oh, okay.
The one they're not giving you is this one from the calculator. So just know that it has everything to do with the way it's phrased. For example, if I say, what is the cosine of root 3 over 2, I am talking about the first quadrant only.
Okay.
So it's 30 degrees.
Yeah.
By definition, I'm talking about the first quadrant only. If I said, what is the cosine of negative root 3 over 2, I am by definition talking about which quadrant?
The second one?
Yeah, 150 degrees. That's the answer your calculator will give you, right there, only, for this problem. Even though we also know that in the third quadrant, it's also true. In other words, if I give you this equation, now it's a whole different story. You don't use your calculator to solve it. you find the two places in the unit circle where cosine is negative and figure out the correct reference angle, which is 30 degrees. But in this case up here, we know that that occurs in the second quadrant, so it's 150 degrees, and it also occurs in the third quadrant.
But I just put in my calculator and I didn't get 150 degrees.
Are you still in radian mode?
No.
You switched it to degree mode?
Yeah.
What'd you get?
I got 0.999886.
And you're talking about, you put in this.
Yeah.
Inverse cosine of that ratio, not the cosine.
Oh, no, I put in the inverse.
Yeah, you need the inverse. Yeah, I maybe wasn't clear enough. In other words, in our original equation, we know what the cosine of x is, but we don't know what x is. And the way to get x is to take the inverse cosine of both sides.
Okay, now I got 150.
Okay. But you didn't get the 210. It's never going to give you that one. So it's telling you the domain of x is 0 to 360 degrees. You need both of these.
Yeah.
You with me? And,
yeah.
And that's really significant because that can be quite confusing to a lot of people. The fact that you don't get the same thing out of your calculator as you get when you're solving an equation and you have to come up with that other angle in the unit circle. Because when you're given a statement like that, there are almost always two angles in the unit circle that satisfy that.
Yeah.
The only ones that don't are when you say the cosine of x equals 1. There's only one place in the unit circle where that happens, and that's at 0 angle, 0 degrees.
Yeah.
Doesn't happen at 90, doesn't happen at 180, and doesn't happen at 270. So whenever you have an equation like this that's equal to 1 or negative 1, then you're only going to have one answer for x.
Okay.
Any other angle that is not a quadrangle, you're always going to have two of them.
Yeah.
All right. You got any equations? Let's see. Should I look and see if I've got an email from you?
Yeah.
Yes, I do. Okay. Let's see if I can pull that up a little bit. Okay.
Yeah. I just wasn't sure how to write the equations.
Okay.
Wasn't sure, like, what format it should be in or anything, really.
Well, let's think about this for a second. We're looking at the upper half of a circle. Now, if I wanted the equation of that not being in parametrics, well, I know that, hold on a second. The circle at the origin has this equation. That's 2. 2 squared, right? In other words, x squared plus y squared equals r squared.
Yeah.
You solve that for y, you get this. The plus side is the top half of that circle. The minus side would be the bottom half.
Okay.
Okay? So first of all, that's the xy. That's not parametric equations yet.
Yeah.
However, I think that will lead us to there.
Okay.
you can create parametric equations from a single equation. There's our, whoops, here's our single equation. And we're only looking, for doing number A, we're not looking at the negative, we're only looking at the positive.
Yeah.
So there's our single equation that uses only x and y by letting x equal to t and changing y to a function of t by replacing x with t. Okay, so here's my parametric equations. There's one of them. I'm going to erase that plus sign because it looks too much like a t.
Okay.
Okay, now
Yeah.
x equals t, which is what they tell us to do. Well, then now let's rewrite y. Y must be equal to the square root of 4 minus t squared. There are your two parametric equations. Where we started with y was a function of x, we now have x as a function of t and y as a function of t.
Yeah. Okay.
And there's a reason for that. I mean, it sounds a little silly. Why start with two variables and now I got three and two equations instead of one? And the reason is that parametric equations model parabolic projectile motion beautifully. In other words, if you throw a stone straight up into the air, it goes up and comes right back down. It's hard to see that in an XY plane, right?
Yeah.
If I throw a stone straight up in the air, it goes up, comes right back down. I just got a line. I can't see what's happening. But if I have the y motion be a factor of t, and the x motion be a factor, then it looks like parabolic motion. And this is with time instead of x. This is the height, or the y value on the stone. And instead, it's going straight up in the air, but it takes a while to hit its height. And then it comes back down and hits the ground. And parametric equations describe this motion so much better than without parametric equations. As I said, if I'm using just x and y, it just looks like a vertical line. I can't see what's going on. But if I can express y as a function of t, now I can see what's happening to that stone, its height, based on time.
Okay.
So parametric equations are extremely valuable. And that's the reason we can switch back and forth between parametric equations and rectilinear. Now, there's also something they call an arrow. Time only goes in one way. So,
Yeah.
I don't know if they've taught you this or not, but when you are graphing parametric equations, it is actually correct to put that arrow on there.
Yeah.
Okay?
I don't know which direction it should be in.
Right. And what that means is as time counts from 1 second to 2 seconds to 3 seconds, the points on that curve do this. In other words, that curve is traced as time passes. In other words, after 1 second, it's done that. After 2 seconds, it's done that. After 3 seconds, it's reached its height, and then it starts coming back down. And so that arrow tells you which way you are tracing out that curve.
Oh.
Okay? Now let's look at one that's slightly harder.
Wait, but can it have two different answers? Because the answer key says something else.
What's the answer key say for A?
For A, it says x equals t and y equals 2 times the square root of 1 minus t over 2 squared.
That's going to be the same answer. Tell me what they say again for y and t. I'll do it algebraically to prove it to you.
Okay, so x equals t and y equals 2 times the square root of 1 minus t over 2 squared.
And all of that is in the numerator?
No,
And
it's
all
just,
of that's under the radical sign?
but the t over 2, like the 1 is not divided by 2.
Okay, so here, let me
And
make sure I get it written properly. Not sure why they rearranged it, but so it was 1 minus
1
t.
minus, then t over 2 in parentheses. So the t over 2 is both squared.
Like that.
Yeah.
Okay? So let's perform that operation. We get 2 times 1 minus t squared over 2, right?
Over 2 squared, right?
Excuse me, over 4, yeah.
Okay.
Okay. Now I'm going to take that 2 that's outside, and I'm going to bring it inside the radical as a 4.
Okay.
It's going to give me 4 minus t squared.
Oh.
That answer is the same as this answer right here.
But why did they write it so weird?
I don't know. That's a good question. I'm not sure why.
Okay.
It certainly isn't the easy way to write it, because if you're going to let, in other words, perhaps they didn't solve for the equation of the circle like I did.
Yeah.
Because if they solve for the equation of the circle, then it's a simple process to let x equal t, therefore y equals the square root of 4 minus t squared.
Yeah. I don't know. I think your way.
I'm not sure why either. They may have another way of doing it, but my way works perfectly fine. It may not work so fine for D. Yeah, it will. D is an ellipse. Okay? But first of all, tell me the equation of that circle that is in B, because that one's not at the center.
In B?
Mm-hmm. So if I said, give me the equation of, I'll go ahead and complete it. Now give me the equation of that circle.
Oh man.
Remember, the general format when it's not at the center is this.
Y squared? X minus h.
Y minus k equals r squared. Okay? So, fill in what's...
X minus 2.
Okay, so it's x minus 2 squared.
Plus y squared.
Equals 4.
4.
Okay, so now we got to solve that for y. So I'm going to take that stuff over to the other side. So I got y squared equals 4 minus the quantity x minus 2 squared. And I'm going to take the square root of both sides. And since I'm only dealing with the upper half of the circle, I'm only going to use the positive square root.
Yeah.
Now, do I want to expand that? I'm not excited about it. I can leave it like that.
Okay.
And so I have my equation for the upper half of this circle.
And x would equal t?
Yep. The rest of it's a piece of cake. In other words,
Okay.
X equals t, therefore y equals the square root of 4 minus t minus 2. In other words, wherever you run into x, substitute t.
All right.
Now,
I think
probably your answer key is probably going to give you something different here also, because I can expand that out. I can foil the t minus 2, and then I can combine the 4 with one of those, the constant number, which is going to be plus 4. So that actually the numbers are going to disappear. And I'm going to end up with minus t squared plus 4t, I believe.
They say that x equals t plus 2. Is that right?
Ah, okay. Well, here's the thing. You can actually let x equal whatever you want.
Okay.
And in this particular instance, it actually makes the y part of it a little bit easier. So they're going to let x equal t minus 2. So now y becomes the square root of 4 minus t squared. Get it?
Minus 2 from the x minus 2 went to
Well,
the...
yeah, exactly. In other words, that way I don't have to FOIL that out. By letting x equal t minus 2, now I can just substitute t wherever I am looking at x minus 2.
Okay.
So it makes the y equation a little prettier, and it makes the x equation a little bit less pretty. In other words, x equal t is the simplest, but x can equal anything. And y can equal it. Well, it depends. If x equals something a little more complicated, then y can equal other stuff. Do you have one? Let's see. We would do C the same way, only we would figure out what the equation of that circle is and use the negative radical of it, because we're looking at the bottom half of it.
Yeah.
D is the top half of an ellipse. So you would use the equation of an ellipse. In other words, it's an ellipse with the center there, and the equation of a horizontal ellipse is x minus h squared over a squared plus y minus k squared over b squared. All of it's equal to 1.
Yeah.
Okay. In this particular D, the center is at 0, 1. So it's going to be x squared over a squared plus y minus 1 squared over b squared equals 1. And we can measure what A is. A is 4 units. So it's x squared over 16 plus y minus 1 squared over B looks to be 2 squared, which is 4. So there's our equation of that ellipse. Now, if I solve for y, which is what I've done on all these others, you can see what you'd have to do to solve for y. It's a little harder when you're talking about an ellipse. But you want me to go ahead and finish this one?
Yeah.
Okay. So if we solve for y, let's see, we get y minus 1 squared equals, over 4, equals 1 minus x squared over 16. I multiply everything by 4, that becomes a 4. I get rid of that 4, and that becomes a 4. With me?
Not really.
Well, as long as you can start there, then it's an algebra problem.
Yeah.
In other words, what you're doing is solving for y. For some reason, I'm trying to write off the screen. That's the formula you're starting with. The formula for that ellipse. And the next step I'm going to do is take the square root of both sides, which solves for y minus 1. And I'm going to take the positive end of the radical because I'm only looking at the top half of the ellipse. I'm not looking at the bottom half. So just I understand you're a little confused on it, but I don't know where to start. Let me go ahead and finish solving it. I get
If you have a
y minus 1
one, 4
equals,
on the bottom of the other.
what's that?
You have a 16 on the bottom of one, but a 4 on the denominator of the other.
That's because there was a 4 on the denominator and I multiplied both sides of the equation by 4. That's how that 1 turned into a 4, and that's how that 16 turned into a 4.
Okay.
You got it? In other words, take this equation, multiply both sides by 4.
Yeah.
Gets rid of this 4, turns that one into a 4. Okay? So, back to where we were, let's see. Y minus 1 squared is equal to 4 minus x squared over 4. And this time, well, I'm thinking I may want to let x be, let's see, if I let x be t, I'll still have a y. In other words, you have choices on what you can let x be. You can let x be anything you want. You can let it be the square root of t minus 1. You can let it be t squared. You can let it be t. It's your choice. I'm not sure what methodology you're supposed to use for determining what x should be. These instructions are pretty clear. Let x be t. And yet the answer they gave you, that's not what they let it be. They let x be t minus 2 in that previous problem.
And here they said x equals 2t.
Okay, so if x equals 2t, now whenever I find x, I'm going to substitute 2t. Okay, so let me create some room over here to write. Let's see, you can usually figure out why they let x equal 2t, okay? Because it's going to make y look a little prettier. Okay, so therefore, y minus 1 equals the positive square root of 4 minus, instead of x, I'm going to put 2t in there, squared over 4. Now what is that? Y minus 1 equals the square root of 4 minus 4t squared over 4, which is t squared.
Does the negative distribute?
No. In other words, first of all, you square the 2t, which is 4t squared, and then you cancel out the 4's, and you're left with a negative t squared. Okay? And now, if I want to solve for what y is, then I just add 1 to both sides. So y would be the square root of 4 minus t squared plus 1. And that's y, and that's 2t. Now, again, I don't know how to figure out that 2t works better than t. And I say it works better, it just makes y look prettier. Because y is going to look not so pretty. If we make x equal t instead of 2t, then all this super simplification that we did won't take place. And we'll have a lot more complicated thing inside the radical sign.
Okay.
Not sure why the rules state that y should look simplified and x not. But that appears to be what they're doing here, despite their instructions to say let x equal t. You can let x equal t always. You just get a more complicated expression for y. Okay?
Yeah.
Zoe, are you good to go for this evening?
Yeah.
I know it can be confusing. Parametric equations can definitely be confusing. But just kind of treat it just use the same method. In other words, regardless of what their answers were here, you could have come up with 2 completely correct answers by just letting x equal to t on all 4 problems.
Okay,
You'd
that's
have just
good.
had a more complicated looking y, but it still would have been correct.
Okay.
There are literally an infinite number of combinations when you go to parameterize a single xy equation. You have literally an infinite number of solutions. You can let x equal t, you can let it equal 2t, you can let it equal 1,000,000 t. Each one of those will give you a different solution for y.
Okay.
Okay? So
Yeah.
hopefully that's helpful.
Yeah.
And
Okay.
I will let you go.
Okay, thank you so much.
You're welcome, Zoe. Talk to you next time.
All right, thank you.